That's right. Friday, we were adding every time. It was an arithmetic mean or arithmetic sequences we were finding. Today, we're multiplying every time, and they are called geometric sequences. So you want to open up some notes, label them 10-3, geometric sequences. Very, very much like Friday, except instead of adding, we are multiplying. Gesundheit. 10-3. So this would have been the first 6 terms of your geometric sequence. Now Friday we had a D value, which was a common difference, which you could take by finding any term and subtracting by the previous term, and you have what you're changing every time. Today we're going to call that R, the common ratio. And R for this geometric sequence would have been 3. You take any term divided by the previous term, and you should get your R value. If R can be a fraction, if it's getting smaller, for instance, if this was going in reverse order, R would be 1/3, getting smaller. So, and it can also be negative, alternating signs. All of that is possible. First slide. Write the first 5 terms of each geometric sequence. Well, we did one just like number 1 in the DOM. Let's look at number 3. So the first term is 20, and our R is 1/2. So that'd be 20 times a half, 10 times a half, 5 times a half, 5 times a half again, and there would be the first 5 terms. You just keep multiplying by your common ratio, your R value. What about number 7? What do I do on number 7? It is a recursion formula. And what were you saying, Troy? That's right, -6, and then I plug that in for this term, right? So it'd be -5 times -6, 30, -5 times 30, -5 times -150, -5 times 750. Yeah, I'm going to need help with that one. I think it's -3750. I'm just going to guess since nobody's going to tell me. Yeah, -3750. Remember, these recursion formulas, you're not actually subtracting 1 from anything. That just means if this is your current term, what was the previous term? So remember that. Questions on this slide? If you remember from Friday, we had 2 formulas. We had the general term formula and we had a sum formula. Well, same thing today. General term and a sum formula. And we're actually going to have one more toward the end of class, toward the end of the lesson, but these are the first 2 for now. The general term formula for a geometric sequence and the sum formula for a geometric sequence. I didn't mean to cut you off. Okay. Use the formula to find the general term that is asked for. So let's just jump straight into a hard one. I'm not going to be that guy and count the 2 seconds. All right. Well, you weren't kidding. All right. Let's jump straight into a hard one, like number 13, because I don't think anybody actually wants to do this to the 1,000th, or in this case, millionth term. So the formula was it a sub n equals a sub 1 times r to the n minus 1. Is that right? So we're looking for a sub 1,000. A sub 1 is... Oh, I'm sorry. We're looking for the 40th term. Oops, my bad. We're looking for a sub 40. A sub 1 is 1,000 times the r value to the 40 minus first, so to the 39th term. You can punch that in your little calculadora. 1,000 times negative a half to the 39th power. How really small? Holy mackerel. You know what? I like you putting that in scientific notation. That's how I'm going to do it too. Here. Okay. These things can get really small really fast. Try 15. Try 15 on your own. What'd someone get? 0.1. Did anybody get something different than that they'd like for us to take a look at? Alrighty. Moving on then. That's the general term. Just like on Friday, we're now going to find the general equation and then use that to find the seventh term. So, 17, what is my R value here? 4. Yeah, take any term, divide it by the previous term. So, we're looking for a sub n, which is a sub 1 times r to the n minus 1. Well, since we don't actually know, we're just finding the formula, so you can leave n in it. Any questions about where I got this formula from? Okay, now we need to find the seventh term. So a sub 7 equals 3 times 4 to the 6. Punch it in, blurt it out. Thank you, sir. Anybody get something different than that? Alright, try 23. Try 23. First things first, what does somebody get for their R value? Negative 10. And then a sub 1, oh dang, I didn't need left space. It's 0.0004, negative 10 to the n minus 1. And when you plug in 7 for n, you get 6. Oh, no, I was meaning the actual answer. When you plug in 6, what do you get? Or 7? Negative 400? Did anybody get something different than that they'd like for us to look at? Alright. Clicking. Questions on this slide about what you're asked to do. Okay. Click. Sometime use the formula for the sum of the first n terms of a geometric sequence to solve. So, number 25, the sum of the first 12. All right, anybody have this formula written down right in front of them? What was it? S sub n equals... Well, thank you. So here we go. We're looking for S sub 12. A sub 1 is 2. 1 minus, what's my R value? 3 to the 12. All over 1 minus 3. Yikes. I'm about to boot up the old calculator myself. So 2 times 1 minus 3 to the 12 divided by negative 2. I'm getting 531,440. Somebody get something different than that? Sweet. Probably the hardest part is just finding out what your R value is. But as long as you remember that you can take any term and divide it by the previous term, like some people are so obsessed with making it the first terms. Well, sometimes dividing the first two terms isn't the easiest way to go. So just look for two easy terms to divide. 12 divided by negative 6, negative 2. Bam, there's your R value. Try number 27. Try 27. Yes, ma'am. Get this? Yes. Jared, what'd you get? Josh, what'd you get? 2,049. Anybody get something different than that? Good job. Any questions from this slide? Click. Indicated sums. Okay. I always thought these were interesting because if you remember on Friday when we were talking about arithmetic sums or sequences, even though we were adding every time, wasn't it the number being multiplied by the number that actually gave us our D value? It's funny because when you're looking at summation, whatever kind of sequence you're looking at, it's like one step more complicated than that gives you your common D or R. Addition, we actually need a multiplication to find our common D value. I'm telling you all that to get, what do you think is going to be your common R value on number 31? What does somebody think might be our common R value on 31? Let's look. Let's plug in our first three terms for 31. 3 to the first, oh come on, oh geez, is 3. 3 to the second is 9. 3 to the third, 27. What's our R value? 3. So for geometric terms, even though you're multiplying, it's actually the number being raised to an exponent of your variable that gives you your R value. So I always thought that was interesting, that it always takes like one step up in complexity to give you your common ratio. So use the formula for the sum to find the first n, no, oh, well, we know what n is. To find, in our case, the first 8 terms. So we're actually looking for S sub 8, A sub 1 times 1 minus, our R value was 3, come on, board's messing up today, I'm going to do this better. S sub 8 equals 3 times 1 minus 3 to the 8th power, all over 1 minus 3. Punch your in, let me know what you get. 9,840. If somebody like to contest that answer. All right. Very good. What do you think is going to be our R value on 35? What do you think is going to be our R value on 33? Right, the 2, because it's the one being raised to the exponent. Now let's look at our first few terms real quick. So if we plug in 1 for this, that's 5 times 2 to the first. Plug in a 2, 5 times 2 to the second. Plug in a 3, 5 times 2 to the third. So the 8 times 5 is 40. And you can see you're multiplying by 2 every time. Anything else happening in the problem only affects really your first term. Down here, you plug in 1, 1/2 to the second power. Plug in a 2, 1/2 to the third power, 1/2 to the fourth power, etc. Let's actually finish 35. S sub 6 equals A sub 1, which is actually 1/4, times 1 minus R, which was 1/2, raised to the 6th power, all over 1 minus 1/2. Bring up our old calculator. 0.25 times 1 minus 0.5 to the 6 divided by 0.5. That's what I got. Did somebody get something different than that? It doesn't tell us what decimal place to go to, so I'm going to go 0.49. Okay, questions on that? Only one thing left in this lesson. I always kind of enjoyed this topic. Theoretically speaking, purely theoretically, if I started a foot from this wall and I went half the distance to the wall every step, theoretically would I ever touch it? No, because I would never actually get to 0. I'd be 1, then 1/2, then 1/4, then 1/8. And technically speaking, I would never touch it. But I think we can agree that anytime you're making something smaller like that, eventually, like the DOM, instead of multiplying by 3 every time, what if I said multiply by 1/3 every time? You have 1, then 1/3, then a 9, then 27. And eventually, you'd have like 1 over a billion, then 1 over 3 billion. And it'd be like throwing a grain of sand on the beach. You wouldn't really be changing anything. When you have a sequence that is getting smaller, which can also be worded as whenever you have a sequence where R, the absolute value of it, is less than 1, so 1/2, negative 1/2, 1/3, negative 1/3, anything where the actual value is less than 1, you could actually have an infinite sum. You could say, count up all the terms that will ever exist in that and tell me what it all equals. And even though theoretically it wouldn't exactly equal that, because the numbers would eventually be so small they wouldn't really even change anything, you can estimate that sum. And you can do that, hopefully, yeah. I didn't include the slide? I didn't include the formula. Okay. And you can do that using this formula. It's actually a very simple formula. S sub infinity, an infinite geometric sum, is just A1 over 1 minus R. Very simple formula. The first term divided by 1 minus R. And that is if and only if your sum is getting smaller. Ye be warned, there's a very good chance that on your test I'll ask you 2 infinite sums. Okay? One of them will be something like this. Another one might be like 1, 2, 4, 8, 16. Something that's getting bigger. And I'm going to want you to acknowledge and realize, hey, if your numbers are getting bigger, meaning your R value is greater than 1, you can't find an infinite sum because it's just going to keep getting bigger. You can only find an infinite sum if your R value is less than an absolute value of 1. So, let's look at 37. What's my R value? 1/3. Very good. Any term divided by the previous. So, it's less than 1. I can find the infinite sum. S sub infinity will be a sub 1 divided by 1 minus your r value. And there you go. So that's 1 divided by 2/3. Flip and multiply. And that's the same as 3/2. The sum of that infinite sum is 3/2. What is the r value on number 39? What's 3? What was it? Very good. Very good. 1/4. 3/4 divided by 3. You know, that's how you find your r value. Would give you 1/4. You could find that one. What's going to be the r value on 43? What's going to be my r value on 43? What's that? That's right. It's going to be the number being raised to the exponent. And we'll find the first two terms real quick just to prove that again. If you plug in 1, that's 8 times negative 0.3 to the 0 power. What's anything to the 0 power? 1. So 8 times 1 is 8. Plug in 2. 8 times negative 0.3 to the second. I'm sorry, to the 2 minus 1. So 8 times negative 0.3, etc. Divide, you do get negative 0.3. So S sub infinity of 43 is a sub 1 divided by 1 minus your r value, and you can punch that in the calculator. Has anybody punched this in the calculator? Should be 8 divided by 1.3. 6.15. That sounds about right. Anybody get something different? Infinite sums. Easiest formula of the day, which I think is funny. Because it sounds like it'd be complicated. I believe the only thing left is a few more examples of that. Express each repeating decimal as a fraction in lowest terms. Oh, these are fun. Okay. The whole premise of these is you can rewrite any repeating decimal as a fraction using that infinite sum formula. Here's the premise behind it. Let's look at 47. Okay? Which I think is funny. They actually use the number 47. Never mind. Okay. Right? Isn't this the same as 0.47, 47, 47, 47, 47, etc., right? Etc. Well, they're like, hey, couldn't you break that down into 47 over 100 plus 47 over 10,000 plus 47 over 10 million, or excuse me, over a million, etc. Couldn't you just break that down into all the little 47s added together? Yes, you could. Well, if you write it down like that, it's nothing more than a geometric sequence. You could take any term divided by the previous term. So 47 over 10,000, divided by the previous term, 47 over 100. Flip and multiply. Happy place. Okay, I'm going to do it over here. 47 over 10,000. Flip and multiply. Cancel, cancel. Cancel, 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 cancel. You're left with 1 over 100. Right? Then you have your r value. That's your r value of an infinite geometric sum. So you have a sub 1, which was just, I'll just put it as a decimal, 0.47, 47 over 100, over 1 minus r. Now, if we were to subtract these as fractions for a moment, wouldn't this just be 100 over 100 minus 1 over 100? Yes, it would. So that'd be 0.47 over 99 over 100, which could be written like this, right? How does this reduce? Anybody remember if you have two fractions? Yeah, you could multiply the top and bottom by 100 and just get 47 over 99. Here's the shortcut to these. You don't have to do this every time. I'm just trying to show you why what I'm about to show you works. You could do this for every problem, every single one of them. But instead, here's the shortcut to it. If this did not have a repetend, well, how would you read this? 257 what? Thousandths. Here's the whole shortcut. Subtract that by 1. And reduce if you can. Any repeating decimal, if you take the part that's repeating and put it over basically that many 9, you've just rewritten it, that repeating decimal, as a fraction. I don't think that reduces. I could be wrong. Good. And that's it. So real quick, try this one on for size. See if you can do it. What would 0.1369 repeating be as a fraction? Just raise your hand when you think you know. Seamus. Denominator. And again, I don't think that reduces. I hope not, because I don't want to do it. But very good. And even today, I guess I don't care if you reduce or not. But just know that on your test, it's probably going to put the answers in reduced form, so it may not match up perfectly. Very good. Questions? All right then. I don't remember what this last slide is. The general term of sequence is given. Determine whether the sequence is arithmetic, geometric, or neither. Ooh, fun. So, easiest way to do this, it just wants to know what kind of sequence is it. Just look at the first few terms and it should be very clear to you. Let's look at 51. If we plug in 1, 2, and 3, you get, if you plug in 1, you get 6. Plug in 2, you get 7. Plug in 3, you get 8. What kind of sequence is this? Arithmetic. And our D value would be 1. Very good. It wants the common difference or ratio, so D equals 1. Let's plug in 1, 2, and 3 into this. 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. What kind of sequence is this? Geometric. And what's our common ratio? Very good. Let's come down here. Plug in a 1. That's 1 squared plus 5. 2 squared plus 5. 3 squared plus 5. 4 squared plus 5. What about this one? It's a neither. If it's not going up by a noticeable addition or multiplication pattern, then it's neither. So you just write neither, and you don't have anything else on it. Any neither, you have to have a formula for. You can't just have it off. Very good. Questions? All right. Here you go.